nucleophilic attack and depronation. Base like sodium hydroxide, they are strong already, so they can attack right away. Okay. All right. So we have the acetal formation, cyclic acetal. We have cyclic thioacetal. You can add a hydrogenation, and with raining nickel, remove the aldehyde ketone. Okay, altogether. Nitrogen nucleophile. We have two types. So we have primary amines. The first, third, and fourth. Okay, this is a primary amine, making an imine. If you don't know the name, it's fine. Secondary amine, making an enamine. Okay. All right, down here is the last reaction we learned yesterday from we call this hydrazone. If you add the strong base, okay, and heat, we call this Wolff-Kishner reduction, just like the cyclic thioacetal, remove the ketone or aldehyde. Okay, and these are the mechanistic pattern in both conditions. All right. Now what? Remember the use of ethylene glycol? We use as a protecting group. Okay. You won't get to use it yet on exam 1, so you won't. But we still use its mechanism. They are in equilibrium. Are you following on that? Okay. And last time we talked about how to control equilibrium. If you want to go forward, get to the product acetal, you use ethylene glycol or alcohol in general as a solvent, drive equilibrium forward. If you want to go backward, what do? You don't add alcohol, you add a bunch of water, flood them out. Okay. This is a reverse reaction. All right. Today we're going to talk about hydrolysis. What does hydrolysis mean? Like by its name. Hydrate. What does it mean? Water, right? Lysis means cut. Okay, we cut the bond with water. You will hear the term hydrolysis very, very often especially in biochemistry. A lot of the enzymes that undergo hydrolysis we call hydrolase. Okay, that's an enzyme. Anyway, all right. So we're going backward from acetal, from imine, from enamine. Anything you learned yesterday can go backward. That's what we're going to do today. Okay, and now you can see that what reagent we add? Water, and water. See that? We're gonna flood them all out. Okay, and we use acid as a catalyst. All right. And go back one slide right here. If you remember, the protecting group is stable under basic condition. Okay, so we use acid to remove them. Okay, under basic condition, it doesn't do anything. Okay. All right. So since we use water and add small amount of, let's say, sulfuric acid. Okay, so the proton source, can we agree on that? Is this guy. Do you understand what I just said? Should you use sulfuric acid as a proton source? No, why not? Tell me, explain, but why not? It's small. One is small amount, like catalytic amount, right? So there was a catalytic amount, see that? And two, strong acid dissociate 100%. You don't have that in the solution. Does that make sense? Okay. So who's gonna pick up the proton? Water. So lots of water. It's a solvent. Lots of them. Okay. All right, when you draw hydrolysis, so we're going backward. We're going backward now. I'm going to show you forward first. Are you familiar with this? This is forward, see that? All right, walk me through it. We're going to warm you up so I know this is in the morning, okay? What do you call this step right here? Pronation, next one. Nucleophilic attack, next one. Depronation. All right, open your mouth, next one. Pronation. Loss of living group. Depronation and nucleophilic attack and depronation. Okay. All right. We're gonna trace back every single step. If the forward is depronation, guess what's the reverse? Pronation. If the forward is nucleophilic attack, going backward, what is it? Loss. Can you see this guy? When you go backward, this guy has to leave. That's a loss of living group. If the forward is loss of living group, water coming off, going backward, what happened? Nucleophilic attack. Can you imagine that? Every single step we trace backward. Let me show you. Okay, this is the hydrolysis of acetal. So start with acetal, go back to hemiacetal, and go back to the regular aldehyde ketone. Okay, so the first step, so add an acid. First step, always pronation. Okay, so the forward is depronation, so we're going backward now, so it's pronation. Okay, and the same thing. All right, so we have loss of living group. Okay, nucleophilic attack. And the last step is depronate that guy. You stay with the neutral molecule. See that? Okay. All right. We go from here to there. Now let's look right here. Okay. I don't want you to memorize it. Okay. Go forward and go backward. It's gonna revert. I don't want you to memorize like that. I would rather you see what's going on and guess what's happening. Okay. Now from hemiacetal to ketone. This is acetone. Who has to leave? The methoxy group, the hydroxyl group. The methoxy group, that oxygen right there in acetone is the water, the hydroxyl group. You know, this guy has to leave. If you want to make it leave, what do you usually do? Pronate it. Is it a good leaving group right now? No, that's why you have to pronate it. And it's gonna go with the same pattern. Okay, now what? That's a good leaving group. Now, do you know how to make it leave? Yeah, use a lone pair on oxygen and kick them out. You know? And the last step, you know what to do with it? Depronation. This is a strong acid, won't survive in the solution. You gotta depronate it. That's the mechanism makes sense. It gotta make sense. Okay. So again, this class teaches you how to be reasonable, how to think logically. We do the same thing with imine. Okay. Again, the same thing. If you look at the reaction mechanism of imine formation, we just trace backward, okay? But I don't want you to memorize that. It's just like going backwards, just memorize lots of the group nucleic acid. It's just memorizing. Let's look what's going on here and what you have to do. It tells you, okay? All right, so can you see that nitrogen has to leave? Everyone see that? Nitrogen have to leave. If you want to make nitrogen leave, what do you think you have to do? You have to pronate it. Why do you have to pronate it? Let's talk about why. Convert this guy to a better living group. Does that make sense? It's a poor living group, just like an alcohol. Same thing there. Okay. All right. So first step, pronation. I use the hydronium ions. Not sulfuric acid. Okay. It doesn't exist in here. All right. Next one. What happened? Go from here to there. You have to go pass through carbinolamine. There's an alcohol in it. Carbinolamine. Okay, there's an alcohol. We need an oxygen, right? How do you add an oxygen? Nucleophilic attack. Who's attack? Who attacks? Good job. Water. It's a bunch of water. Water attack. See that? Okay. Now what? Almost there. What do you do with that? Right there. Depronation. That's a strong acid, so depronated. Halfway done. Carbinolamine. Okay. All right. We're gonna go from carbinolamine all the way to acetone. Okay. All right. Who has to leave? Nitrogen or oxygen? Nitrogen, what do you do with it? Pronate it, pK 38. When you pronate it, pK 10. How many times is that? 38 and 10. 38 and 10. 10 to the 28th times. How better that is. See that? It looks like it's nothing on paper, but number-wise, math-wise, from pKa, was it 38 to pKa 10. 10 to the 28th times better living group. Why won't you do that? Okay. All right. So we do that. So all right. Now kick them out. How do you kick them out? The lone pair on oxygen. Okay. And then depronation. Follow the logic. You got to think. If you've never done it before, it's time to practice thinking. If you don't think, guess what? On exam, if you see a question like a mechanism that you've never seen before, you can't do it. Okay, so try to practice that logic now. All right, last one is enamine. Okay, enamine is slightly different. Now look right here. This is review. This is going forward of enamine. Okay, we're gonna go backward right there. Look at the last step. Everything else the same thing with the imine. So I'm not talking about anymore. The difference is just the last step right here. The last step is the elimination. Can you see that? This is the alpha position of the functional group. There's an alpha position, so we pull proton from the alpha position. Going backward, you're going to add the proton back to the alpha position. Does that make sense to you? Okay, that's evidence of why you have to do this first. Let me show you. Okay, look right here. This is enamine. That's an acetone. Okay, there's 2 protons right there. Can you see that? In the product, there are 3. You pronate on that position. Okay, so pronation occur on that position. All right, first step is a pronation. Just that position right there. That's pronation reaction center. That one. Okay, you can use the lone pair on nitrogen coming down to. It's fine. I'm just showing you resonance structure. It's fun. Just show you that carbon is positive, but you don't need to. You can put these 2 arrows to get 3 arrows together in one step. It's fine. You're gonna get right here. Okay. Anyway, all right. Next one. So adding water. So nucleophilic attack. What next? Tell me, help me. The what? You can't say loss of living group, guys. If you do loss of living group, you go back. The what? One more time. Depronation. That's a strong acid. You have depronated. That's carbinolamine. See that? That's a halfway. Okay. All right. Next one. All right. Who has to leave? Nitrogen. What do you do with it? Pronation. Why do we pronate on nitrogen again? Make a doubling group. How much better? From pK 38 to pKa what? 10 to the 28 times better. Okay. All right. Kick them out. Use a lone pattern oxygen. Depronation. Can you see the pattern? They're all the same thing. Okay. Now what? Another skill, related skill, but quite different. Predicting the hydrolysis product. Okay, we're gonna predict the product when you do hydrolysis. All right. Here we go. Here's an example. Watch closely. This is the easiest thing you can do. I'm gonna point out how to do it. Okay. If you don't understand it, this is hard, but it's not that hard. Watch. This is acetal, right? 2 alcohol on a carbonyl carbon. Do you know which carbon in here used to be a carbonyl carbon? Everyone point. Which carbon used to be carbonyl carbon? Everyone point. Where are you pointing? Are you pointing that? Nope, that one, right? Yep. That's the product. How's that? Because alcohol attack right there, that's why you get acetal. If you know which carbon used to be carbonyl carbon, that's the product. Your job is drawing the mechanism of that at home. Does that make sense? That's pretty much it. Identify that carbonyl carbon. Next one. Which carbon used to be carbonyl carbon? The one in the middle. Am I right? Anyone remember what do we call this guy right here? Start with an E. Ethylene glycol. Okay, so that carbon used to be carbonyl carbon. This is cyclopentanone. Did that? And ethylene glycol coming out too. All right. As long as you're not confused by the structure, okay? Sometimes it could be a little bit tricky. Now, next one, right there. Which carbon used to be carbonyl carbon? You know which one? Is it these two? Is it that? That one. Am I right? Okay. Can you draw the product before I show it? Draw them out. Draw them out. You can, and we can check. We call this guy acetaldehyde. Okay, this is acetaldehyde, 2 carbon. We'll talk about naming later. Hey, you have heard acetone, right? The compound name acetone. Okay. Formaldehyde. Have you heard formaldehyde? Yep. Okay, most of you. Okay. This is acetaldehyde, 2 carbon. All right. The other part is ethylene glycol coming out too. You can draw. You don't have to. It doesn't matter. Okay. All right. Next one down. This is enamine. Can you see this is enamine? Which carbon used to be carbonyl carbon? Do you know which one though? It's this one. Used to be carbonyl carbon. Now, what's the product look like? The ketone. That one. Same thing. It's a ketone. I'm going to challenge you a little because people say that you guys are smart. UF students are smart. Is that true? No? Oh my God. I am stupid. Like that confidence. Love that. Okay. All right. I haven't taught you naming yet. Wanna try naming this compound? It's a ketone, right? Yes, I haven't taught you naming yet, but I wanna know if you can. It's a how many carbon? Count that, and it's a ketone in a ring. If you say hexanone, hexane is a long chain, right? It's not a ring. Cyclohexanone. Does it make sense? That's it. That's a naming. I don't think I have to teach you naming, huh? Okay. Anyone want to name this guy? Cyclopentanone. Good job. Okay. At the top one right there. Butanone. Where's the ketone? You got to tell the reader. 2-butanone. Yeah. See, that's it. That's naming ketone. Okay. All right. Summarize it. Okay. So we have the oxygen nucleophile, sulfur nucleophile, nitrogen nucleophile. Okay. All right. We're gonna move on to the top left. This is carbon and hydrogen nucleophile. They do the same thing. All that right there, they do the same thing. Okay. Now, here's the thing. Here's the difference. I put this on this side for a reason. Okay. On the right side, right here, I'm gonna go back one slide. On the right side, the red and the blue. What reaction condition we run them in? Acidic condition. We're moving on to a basic condition. Okay, these are basic condition right there. Not the second step. Not the second step right there. Not that. Not that. That's a second step, like when you're quenching. Okay. Well, this except with the that's an acid, but yeah. All right. Mostly we play on this too. This guy down here. Okay. If you remember the mechanistic pattern of basic condition, 2 steps. What's the first step again? Not depronation. Nucleophilic attack followed by depronation. Okay. All right, here we go. So we move on to reaction number 6. Okay. A lot of you haven't learned this reaction yet. Okay. But did you review on that, this reaction? Did you read the thing I gave you? Okay. All right. So we call this reduction. Okay. But mostly we're going to focus on sodium borohydride and lithium aluminum hydride. What they do, they give you a hydride source. Okay. A hydride source, a hydrogen with a lone pair. Right? Not a proton source. Proton is a hydrogen without electron. Okay, this is a hydride source. Hydride will attack the carbonyl carbon, adding a hydrogen. That's why we call the reduction, adding hydrogens. Hydrogenation is a type of reduction. Okay, that's a proton source. Second step is a proton source right there, or that water, hydronium ion, or that's a solvent. Give you a proton source. Okay. Let me skip that right there. Okay. So here's how it works out. Just watch. You have the mechanism in your hand now. Okay. First step, we take sodium borohydride. So hydride attack. Hydride is a proton with how many electrons? Were you listening? Hydride, how many electrons? 2. Okay. So we take hydrogen with a bond right there. That's a 2-electron attack. One more time. Hydride is a hydrogen with how many electrons? 2 electron. That's a 2 electron. Can you see that? Okay, so that's attack. It's not hydrogen atom. It's not a proton. This is hydride. Okay. All right. So that's a reduction right there. Then pronation with whatever solvent you add, water, ethanol, methanol. That's acidic proton right there. That's it. Okay. All right. One more time. Lithium aluminum hydride. Just the same. Exactly the same. Okay. So hydride. How many protons? How many electrons? One more time. 2, we take that hydrogen and the bond attacking the carbonyl carbon. Make sense on that? Okay. And then second step right there, adding this hydronium ion sulfuric acid in water, pronation. You see the same thing? Okay. All right. Now, what you need to know is, look at how they set up. Sodium borohydride can be added with methanol, water, ethanol, like a proton source. Lithium aluminum hydride cannot. You have to separate them. Can you see that? You have to separate them. Lithium aluminum hydride is one of the most powerful reagent in this course. One of the most. Okay, in this course. If you add lithium aluminum hydride and water, methanol, ethanol, the solvent together, it will attack water or alcohol first, turning itself to an unreactive aluminum hydride, and reaction stop. This is the reason we cannot do lithium aluminum hydride and the next reaction to see Grignard reaction in Florida. You want to guess why? Freaking humid. This guy can even react with the moisture in the air. It's that powerful. Okay, you maybe you have seen maybe in a movie or maybe in the lab. Have you heard the term glove box? That's a big container. They purge like any air inside with the inert gas like nitrogen gas, helium gas in the box. Okay, and when you do experiment, there's a glove thing. You have to like put your hand through it, and you can do things in there. That's a glove box. Okay, so yeah, that's what you have to do. Not the glove box that you pick the gloves out. Not not a glove box. No. Okay. All right. Same thing with lithium aluminum hydride. This is a Grignard reaction. That's a Grignard reagent. Do the same thing. Okay. Very powerful. You're gonna separate it from water, from methanol, from proton sources. Okay. Now you can see two. Can you see this is a two-step too? The strong reagent usually require two-step like this. Okay. Now what the difference is? Go back one slide. Lithium aluminum hydride, sodium borohydride, deliver hydride. Are you following? This guy deliver hydride. Hydride is a hydrogen with how many electrons? 2 electrons. Grignard reaction, a Grignard reagent deliver an alkyl group with a lone pair, carbon ion. Same thing, exact same mechanism. Okay. All right. Let me talk about how to make it first. Start from with the regular alkyl halide, like was it ethyl chloride, propyl, tert-butyl chloride, whatever. Okay. Adding magnesium and ether act as a solvent and a stabilizer. It's that reactive. You need a stabilizer to keep these guys alive. Okay, it's really reactive. Anyway, once you have this, look what happened when you put it together. On paper, it doesn't do anything, but let me explain. When you put the magnesium in on any type of the alkyl halide, magnesium can insert itself between carbon and chlorine. I would like you to look at carbon and magnesium bond. Look at that bond, carbon and magnesium bond. Are you looking at that bond? Is that bond polar? Basic Gen Chem. How do you know a polarity of the bond? How do you know the polarity? Electronegativity different. Do they have electronegativity different? Oh yeah, metal and non-metal. Remember that? Okay, you can look at CMG bond as that. Imagine this replace all the 3 carbon with a hydrogen. That's a hydride. Can you see that? Imagine replace all 3 carbon with the hydrogen. That's a hydride. Just like lithium aluminum hydride, Grignard reagent deliver an alkyl group, a carbon ion. Okay. All right, same thing. Even benzene work as well. We're not doing anything with aromaticity. Stay with aromaticity. Stay. Okay. Doesn't change anything. Magnesium insert itself. That carbon right there, highly nucleophilic. Okay. You can even do with the allylic Grignard and vinylic Grignard. They can do a lot of things. Okay. And the Victor Grignard is a French chemist. This guy got Nobel Prize because the effect, the impact of this reaction. Okay, there's a lot of things. Okay. Anyway, all right. So this is Grignard reaction. Okay. So what do you do? Just like lithium aluminum hydride. So we go from the bond attacking the carbonyl carbon, and then protonation. That's it. Give me the product. Let's go. I miss water. Mercury chloride and water. I miss water right there. Can you add on to it? The last step, bottom right. Mercury chloride, okay, and water. I miss water. All right, eyes up. So first step is protecting group. Are you following on that? We're adding ethylene glycol. So your brain should think like that. Can your brain think like that? Okay, so you're gonna get this. That's the first step. What does PCC do? You know this. Oxidize primary alcohol too. And aldehyde. It have an aldehyde. Okay. Last one. So we have the Grignard reaction. So phenyl only attack aldehyde. Okay. So attack that. And then second step is also the remove the protecting group. It's an acid there. Okay. All right. In B, also protecting group. Okay. But this one is probably this one is the more efficient protecting group. Which functional group does this guy attack? We have aldehyde, we have ketone. You're going to pick one. Which one more reactive? Aldehyde. Now things change, huh? Right? So remember two reasons why aldehyde is more reactive? All right, go review that. Okay. Lithium aluminum hydride. So we got only the ketone left. Okay, attacking ketone. Get that? All right. Hydrogenation with Raney nickel. Remove the cyclic thioacetal. Get that? Adding two hydrogen onto it, basically, like Wolff-Kishner reduction, like Clemmensen reduction. Okay. And down here, mercury chloride is the protecting group. Yeah, for cyclic thioacetal only. All right. Yeah, most of you should feel foggy still. Like, see this reagent? I don't know what to do. It's fine. It takes time. At least you get the practice right here. Okay. All right, we're almost done with carbon nucleophile. Okay. All right, next one, cyanohydrin formation. You don't need to know the name. Okay, but you can see that cyano group attack, nitride attack. Can you see that? Okay. We will use a lot of this reaction in the chapter. What chapter is this? 19. We'll use this reaction in chapter 20. So they put it right here in the textbook. We don't use it yet. Okay, but we use it for why we. I'll tell you in a bit later. All right. So nucleophilic attack, sodium cyanide, right? And then protonation. That's it. That's it. Okay. You can do on the benzaldehyde too. Similarly. Okay. Ketone, aldehyde work as well. Works. Okay. Again, we'll use this reaction in chapter 20 because once you have nitrile CN triple bond, you can make carboxylic acid, all of it. And the next chapter, chapter 20, is all carboxylic acid. So we won't use this in this chapter yet. So we'll use in the next chapter. Okay. You can even add lithium, aluminum hydride attack. You get amines too. You learn amines in the last chapter of this course. Let's summarize the whole thing. Okay. So oxygen, sulfur nucleophile under acidic condition, nitrogen nucleophile also under acidic condition, very similar in terms of mechanism. Okay, top left, this is basic solution. Okay, so this is a carbon nucleophile, hydrogen nucleophile. All right, last two reaction in this course, in this chapter. Okay, so this is a named reaction. When I say name reaction, it means some people's names are on it, like Diels-Alder reaction. Any other reaction, you know? The what? Friedel-Crafts, thank you. Friedel-Crafts, those are name reaction. Okay. Here's the name of these two. We have Baeyer-Villiger and then Wittig. Okay. So the Wittig reaction. When you say it's here we go. So George Wittig, he's a German chemist. It's W, I know. But we say it's like a V, George Wittig. Okay. You might remember hydroboration oxidation, alkene, anti-Markovnikov, BH3, THF. Okay, all right. That comes from Herbert Brown. This guy went to Purdue. I mean, he taught at Purdue. He already dead. No. So, but he was at Purdue. Okay. And he used boron chemistry, got Nobel Prize. His buddy, in German chemist, George Wittig, used phosphorus, okay, and invented the Wittig reaction. They shared the Nobel Prize in the same year. What year is that? 1979. Oh, didn't have Snapchat back then, huh? Okay. All right. Here's a George Wittig. Okay. Look, a lot of confusing, very confusing. But hey, let me point out. Have you heard the term cycloaddition? Yeah. Make a ring, right? Have you heard the term retrocycloaddition? Break the ring. Like a Diels-Alder reaction. This is 2 + 2. Diels-Alder is 4 + 2. Remember that? Okay, very similar to that. Look right here. So we have the reagent right here. Okay, can you read it? Lid, like eyelid. We call it elid. Okay, it's German. Don't ask me why. Okay, it's an elid. Elid, don't call them elide. It's an elid. Okay, so an elid looks something like that. Carbon is a nucleophile. Can you see that? Carbon will attack, just like the Grignard reagent, like a lithium aluminum hydride. This is something with a lone pair attacked. Okay, so attack the carbonyl carbon, and then oxygen will at the same time attacking phosphorus. Carbon to carbon, oxygen to phosphorus. Say that one more time. Carbon to carbon, oxygen to phosphorus. Okay. Wittig reaction work like that. Okay, so carbon attack carbon, oxygen attack phosphorus. You're gonna get 4-membered ring, oxaphosphetane. Don't need to know the name. Okay. Now, breaking the ring. If you remember when you do Diels-Alder reaction, you use 3 arrows. Remember that? When you break the ring, retro Diels-Alder, you use same 3 arrows but going backward. Does that make sense? Okay. So you got a few options. Let me show you. Okay. So you can draw like that, clockwise or counterclockwise. It doesn't matter. You're going to get to the same product anyway. All right. Now look at the product. What functional group are we making? Guys, come on. Look at the product. What functional group are we making? An alkene. We use a Wittig reaction. Two reasons. Okay. 1, extending a carbon chain, and 2, making an alkene. There's a function. That's the application of Wittig reaction, adding carbon chain and making an alkene. When you do synthesis, if you see an alkene, you should think about Wittig reaction, but that's later. Okay. We prepare an elid in situ or in situ. I don't think you guys know this term. Do you? Greek. No, what is the old term? In situ mean you prepare it and use it right away. Like, can you imagine an intermediate? When you draw a bunch of mechanism, there's a bunch of intermediate, right? An intermediate is formed during the reaction. Does it stay till the end of the reaction? No. Intermediate is making it in somewhere in the reaction during the reaction is formed and then get used right away. Similar term right there, meaning right there. most elite is unstable, you're going to make elite in a solution and use it right away. Okay, I'll teach you how to make an elite in a bit. Okay, this is a spontaneous reaction. The driving force is PO double bond. I don't really know how this works, but PO double bond is very, very strong bond, and that's a driving force. That's a physical chemistry. We don't really touch that. Okay, all right. Let's talk about making elite. Okay, when you make an elite, just like Grignard reagent, you start from a regular same old alkyl halide, alkyl bromide, alkyl chloride. Okay, and there's two steps right there. The first step is an SN2 reaction. Do you know SN2, right? Okay, phosphorus attack. See that? Phosphorus just go attack. This is an SN2. Now what? Once we have the phosphonium salt, okay, this is what's going to happen. I think you guys know that the alpha proton is slightly acidic because when you put a proton, that lone pair is resonance stabilized. Okay, phosphorus can do just like that because it's large. It got d orbital. Take a look. That proton right there, you can add a strong base. This is a strong base. You can use anything familiar. Okay, mostly they use sodium hydride or N-butyl lithium, normal butyl like a stretching butyl. Okay, you can use either or. Okay, in a textbook they usually use N-butyl lithium. All right, take that. That's a stabilized lone pair. Okay, these are two steps. SN2 and elimination. That's what they do. Okay, we're going to use this elite to do reaction. Okay, all right, we already have an elite. Any question on making an elite? Let's use it. Okay. Oh, one thing. This is an SN2 reaction. What's the limitation of SN2 reaction? Tertiary carbon, right? That's a problem. You cannot make an elite on tertiary carbon. Does that make sense? You can do SN2. you can do primary carbon, methyl, primary or secondary, but not tertiary. And then you guys, you know this. All right, let's draw the mechanism together. You have that. I don't think you have this in the handout, do you? You do or you not? You don't. You don't have an arrows. Okay, let's draw an arrows. Okay. All right. Who attacks who? You say already. Carbon attack carbon. Oxygen attack phosphorus. Can you draw two arrows? Carbon attack carbon. Oxygen attack phosphorus. Okay. Here's carbon attack carbon like that. Oxygen use the pi electrons attacking phosphorus, not the lone pair. This is 2 plus 2 cycloaddition. All right, two more arrows and we're done. Last two arrows right here and we're done with the mechanism. Okay. This is retro. How do you draw the other two arrows? Go backward, clockwise, counterclockwise. It doesn't matter. Two arrows. So look like that. Okay, you end up with CC. You end up with CC double bond. If you don't know how to start this arrow right here, making CC double bond. Yeah, pull a lone pair, pull two electrons somewhere, making a CC double bond. Okay. Let me walk you through it, how to do it, how to predict the product. Okay. Is this new reaction? It's a name reaction. They got like some unique feature in there, so it could be confusing. Let me explain to you. Okay. All right, this guy's there's a two-step right there. N-butyl lithium is a base. Do elimination, pull a proton. Okay, the most acidic proton is on that carbon right there because when you pull it, phosphorus stabilize it like that. Okay, phosphorus can stabilize at negative charge, the carbon ion. All right, now. You don't have to draw this. The question doesn't ask. I just want the product. Can you make this attack benzaldehyde and draw the product? Give me the product now. Who attacks whom? Carbon attack carbon. Who else? Oxygen attack phosphorus. Do the same thing. Okay. Draw them out. Give me the product. Don't wait for me. Give me the product. Try on your own first. Draw a line between two carbons. Draw the line between oxygen and phosphorus. That's it. And then retro disorder. No, retro 2 plus 2. All right, carbon attack carbon, oxygen attacks phosphorus. You get the a four-membered ring look like that, and then retro 2+2. That's the product. Okay. All right. The other one, this one longer, quite long, but I mean, the reaction set, there are only two reaction centers, am I right? It's a carbon and a carbon. That's the reaction center we're looking at. You can add oxygen and phosphorus 4. I mean, but you know what I mean. The structure might be huge, but it's only two reaction centers we're interested in. What's product look like? Yep, draw the line arrow between carbon and carbon, and then oxygen attack phosphorus. Yep, draw them out. Don't wait. All right, eyes up. Here's a trick. Whatever I have you said, oxygen was carbon attack carbon, oxygen attack phosphorus. I mean, it helps when I draw the mechanism. When you predict the product, you can do just this. Watch closely. I'm gonna redraw the aldehyde right there. Watch. That's the product. Does that make sense though? It's just that. Because the product is carbon attack, carbon and carbon forming carbon double bond. That's a shorthand. Okay. All right. Now we got right here new information. We got Z isomer. You draw, most of you draw E, huh? Of course, I would draw E too because I haven't told you anything yet. Okay. So a Vedic reaction, in this reaction gives you Z, but what controls the stereochemistry? Do right there. I copied this from a textbook. You can see it is not for me. So top two, Z isomers. See that? Bottom two is E. What controls it? What controls the stereochemistry is the type of elite that you use. Okay. Look at the top two elites. These are the top two elites right there. And this is the bottom two. Okay. I would like you to really focus on the negative charge. Which okay, we have negative charge, the top two negative charges and the bottom two negative charges. Which one do you think is more stable? The bottom two. Can you see that though? Why was okay? Look right here. What in bottom two elites stabilize the negative charge? The resonance effect, right? That's the electron withdrawing group. Electron withdrawing group. Can you see that though? Okay. So here's how we communicate. The top two, it's just a regular elite. Okay. We call them an unstabilized elite. Only phosphorus stabilize it. Yeah, it's some stabilization. Otherwise, it can't exist. Right. So the top two we call unstabilized elite. Want to guess what do we call the bottom two? Exactly, stabilized elite. Okay. How to spot stabilized elite? Look for electron withdrawing group nearby. conjugation, basically. Okay, look for resonance stabilization. Yeah, or contain electron withdrawing group. That's it. Okay, there's a reason behind it. If you look at the, if you have my hand now, you flip the next page. That's the reason why the stabilized elite give you E and unstabilized give you Z. Okay, but we're just gonna use it today. Let's see, where's that? Right here. We're gonna practice just spotting types of elite. We got two types: stabilized and unstabilized. Are you following me? Are you following me? We got two types of elite: stabilized and unstabilized. Okay. Look at the top reaction. The first reaction at the top. Look at an elite. Everyone, look at an elite. Now look at the lone pair of the elite: stabilized or unstabilized. Stabilized. How do you know what gives away this is stabilized elite? Can you see the aldehyde next to it? That's the electron withdrawing group. You're gonna be able to spot that. Okay. It is a stabilized elite. What's the major product? E or Z? I'm gonna go back. Oh, no. Yep, E. Yep, right there. E. Okay. This is an E. Stabilized gives you E. Okay. Next one down. Look at an elite. Stabilized or unstabilized? Unstabilized. Okay. Okay. I'm gonna go back one slide. Hold on. Right. No, right here. Okay. This is go back to the first reaction. I forget to tell you. This is stabilized. Can we agree this is stabilized elite? Okay. We are targeting carbon, attacking carbon, attacking the aldehyde. Remember carbon attack carbon? Okay. We are attacking aldehyde. All you do, make this put double bond between this carbon and that carbon. You get that. Make an E. Okay. This aldehyde comes from the aldehyde right here on an elite. Next one more time. Stabilized or unstabilized? Unstabilized. Okay. So this carbon is gonna go attack whom? Ester or aldehyde? Why is this not sure? Have we learned about ester yet? No. The whole chapter, right? What functional group are we learning in this chapter? Aldehyde and ketone. So one more time. Who does this guy attack? Ester or aldehyde? And aldehyde, this guy targeting aldehyde. Carbon attack carbon. But this unstabilized elite, you should get E or Z. Z. This is Z. Okay. Then the last step, just lithium aluminum hydride attack out ester. You get alcohol, but that's next chapter. Okay. Give me the product. All right. We have an elite attacking that compound somewhere. All you have to draw a double bond between them. You just need a double bond between them. E or Z, be careful. It might help if you number the carbons, so you won't lose or gain any extra carbon, or count the carbon, whatever you're comfortable with. Is it stabilized or unstabilized elite? Unstabilized. Okay, so you should get E or Z. Hold on, one more time. E or Z? Z. Okay, Z. Okay, all right. That's unstabilized elite. That carbon attack an aldehyde. Okay, that's a product. Check if you have the same number of carbon. Put number right there so you can see it. Yeah, be careful. Like many students usually just missing a carbon. Okay. All right, here's a question on this one.
There has to be like an alpha.
Ketone, aldehyde or ketone. Okay. All right. The last thing you need to know about this reaction is how to pick an ylide. Okay. In case instance, this is later for exam 3. How to pick an ylide. Look at right here. Ylide is used to make an alkene. Are you following on that? You see an alkene right here, right? So this compound can be made from an ylide using Wittig reaction. Okay. So yeah, we can use Wittig reaction to make this compound. Now to make this compound, you got to pick the right ylide. That's an efficient one, is a less efficient one. I will explain this way. Now, look at the reaction center in Wittig reaction. The reaction centers are between the 2 carbon of alkene. Are you following on that? One side gonna be an ylide, the other gonna be aldehyde or ketone. Think with me. Think with me. If this doesn't make sense to you, nothing makes sense. This is an alkene. You can make Wittig reaction to make this compound because that's what Wittig reaction's for. Okay. The reaction centers are the 2 carbons on an alkene. Can we agree on that? Listen to me hard. Next one. Put your pen down. Listen to me hard. Okay. The 2 carbons of the alkene, those are the reaction centers. One of them is an ylide. The other is a ketone in this case. If you follow me, say I. Okay. I'm going to cut the bond in the middle. Okay. So here are the 2 options. Let's say the right side is an ylide. The right side has to attack that. Are you following on that? The phosphorus attached to it, but that's not the point. We're thinking right now. This is what we're thinking. Don't write this down either. Just think. Okay. That's your option. The other option is the left side is an ylide. Both works. But one of them is more efficient. Okay. And if efficiency doesn't come just this guy attack like that, attack right here, is efficiency come from the making an ylide in this situation. Okay. I'll think right here. If this one, go with the top one. If on the right side, this propyl group is an ylide. Remember, when you make an ylide, there are 2 steps. The first step is an SN2 reaction. What is the limitation of SN2? Tertiary carbon, steric hindrance in general. Does it make sense? Okay. To make this guy as an ylide, you need that triphenyl phosphine to attack that alkyl halide. What type of carbon is that? What type of carbon is that? Primary carbon. Can you do SN2 like that? Please say yes. Yes or no? Yes, perfect substrate for an SN2. Now look at down here. Look at this guy. Okay, down here, that's an ylide. What's SN2 look like now? Attacking what type of carbon? Secondary. Which one more efficient? You go with the primary one. Does that make sense? Okay. So when you write out the synthesis, okay. So fast as on right. Okay. So you're gonna pick that route. You start with that, add triphenyl phosphine, add the base, you get that ylide, and the rest is the same thing. That's how we pick. You don't need to write this down. My point is, I'm just trying to make a point. When you make an ylide, you have to go through SN2. Think with me before you're writing. Think with me. When you make an ylide, you have to go through SN2. Does it make sense? That's an SN2 reaction right there, attack right there. And SN2 is the most efficient if you avoid tertiary or secondary. If there's an option for like primary, you pick primary. Does that make sense? And that's it. That's all I have to say about this. Okay. You got last reaction to go. Now, before I talk about the last reaction, I want you to see this compound. It's big, huh? Huge, right? Okay, that's this is Taxol. It's a natural product, okay? Which means that you can obtain this compound in nature. The nature can make this compound for you, okay? Why is Taxol is important? Anyone know Taxol at all? Have you heard the term Taxol before? It's a medicine. It's used to cure cancer. And trees make it for you. We have trees to make it. Okay. Well, this certain type of cancer can be extracted from some certain type of yew tree. Okay. Let's talk about this type of tree real quick. You can find these type of trees right here in this area. You're gonna go to northeast and northwest, right there, or in Europe. Okay. What does tree look like? Anything have you seen maybe in a movie? The little one. Okay. No, that's the small one. That's like the baby one. Look at the actual one. If you watch the Lord of the Rings, like the old movie, like back in the day. Okay, so those are the trees we're talking about. How long does it take them to grow like that? It's a while. Okay, a while. All right. Now, here's how you get Taxol. You kill the tree. Yeah, get the bark out. That's the bark of the tree, is it not? Extract it. This is chemistry right here. Extract from bark. When you pull the bark out, imagine you, like I strip the skin of you. The entire body. It's not great. Well, the tree dies, right? And this guy, how long does this guy take to grow again? Oh my God. The full one that start producing Taxol is about 200 years. Can we wait for 200 years? Oh no. Okay. Okay. And you take the bark out of the tree. Okay. The tree died. And even the full-grown tree gives you only 0.5 gram. How much is 0.5 gram? 500 milligrams, like your medicine, a tablet, right? That's all you got. Yeah, it's not a lot. And the tree, not even to mention the nature. Who lives on a tree? For example, look at these Hedwigs. You take them home away from them. That's not right, man. Humanity, no. Okay. So taking extracting Taxol from tree is not no, you should not do that. You know, it's not efficient. Okay, and there's a lot of consequences. So chemists try to come up with a way. Hey, can we make Taxol? We can do this. Years and years later, we have 5 ways how to make Taxol. There's a new way now, not on this. Okay, don't quote me on it, but this is an old way. Okay, we can make all this. One way from this, I'm talk about just one of them. Okay, it's invented by a professor from Florida State University. Okay, so proposed in 1994. Okay, anyway, look at right here. Some of you have taken the lab. Many of you are taking the lab right now. You've done some synthesis, right? How many steps? The longest step you ever done synthesis? 1 step, 2 steps? How many steps? You say 4? No. Like how many times you add reagent? Not counting recrystallization, not counting purification. How many steps are there? Paraphenetidine. How many steps? The longest you ever done is 2. The longest you ever done is 2 steps. What's the yield after that 2 steps? You don't have to tell me the number. Is it good? No, of course not. The more steps you have, the lower yield you get. Does that make sense? Look how many steps. Count. 1, 2, 3, 4, 5. Oh no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 steps. 16, 17, 18, 19, 20, 21, 22, 23. Oh gosh. 4, 5, 6, 7, 8, 9, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40 steps. And this one there, 41. Okay. 42, 43, 44, 45, 46 steps. That's Taxol. Give me an idea. What do you think? What happened to the yield? Horrible. You're going to start when you start, they probably start like at 10 kilograms. They probably get like 0.1 gram right there. I don't know. I'm just making up the number, but it's not efficient. See that? But in 1994, this guy proved that we can make Taxol. Not saying it's efficient, but we can. Okay? Now, you're going to make it more efficient. That's what they do. They go back to the tree, the same tree, but they don't look at the bark of the tree. They look at the leaf of the tree. The leaf of the tree, surprisingly, make this compound, which is right there. The very last step, that's Taxol. Reduce number of steps by, I don't know how many, 35 steps. It's a bypass. Can you see that? Okay, so they extract this compound from the leaf. How many is on the leaves? There's too many leaves. This is great. When you pull the leaves out, the tree doesn't die. Does that make sense? Okay, it can regrow the leaf. So extract compound from the leaf, you get that and go 1, 2, 3, 4 steps to get the Taxol. 80% overall yield. Look at that. Now this is how we save lives. Right? Okay. This is organic synthesis. So, but years of research. How would you know that this compound is in the leaf? You're gonna go find it. You're gonna go hiking. Go find it. There's a lot of things in there. Okay. Anyway, all right. Last reaction. Okay, we call it Baeyer-Villiger oxidation. Okay. We use that with aldehyde ketone, adding peroxy acid. Have you heard the term peroxy acid before? Give me one example of peroxy acid that you know or you have used before. Hydrogen peroxide is not an acid. Okay, but close. It's peroxide. What? MCPBA. Have you heard that? Yeah, good job. Okay. Okay. Metachloroperoxybenzoic acid. We'll talk about the name later. Okay. All right. Mechanism go right. Don't do anything yet. Don't do anything yet. Just watch. Okay. So what's happening first? This is an acid, acidic condition. What happening first in the mechanism? Acidic condition. Protonation. Protonation happened first. See that? We start with protonation. Just watch. Just watch. Okay. All right. Now, when you protonate that become a conjugate base. That's a nucleophile. This guy attacking the carbon. Okay. Now, the hardest. This is easy. You have seen before. Protonation, nucleophilic attack. This is like a regular step. Mechanistic step you have seen before. The next step is the hard part. It's new. Really new. You have heard the term rearrangement, have you? This is 1-2 shift one carbon. Okay, one carbon over. Watch closely. All right. You need 3 arrows. So without that oxygen right there forming a double bond. Okay, just watch. And then this carbon right there use that 2 electrons. Oh, I said wrong. That carbon right there, use the 2 electron, hop to the red oxygen. That's a reactive oxygen. And then loss of leaving group. They call it a migration. It's a type of rearrangement. Okay? You end up with this. Like an alkyl group shift. Okay? But no one draw like this. I'll redraw this guy one more time. 1, 2, and 3. That one. Okay, and once you have this, hope you know that you have to depronate it. Can you see that? Okay, depronation. Okay, all right. I have this. I'm gonna leave this on here. I'm gonna have you draw the copy that, but on this reaction. Okay, all right. I'm gonna leave it right here. So just compare contrast. Try to see like where to draw arrows on your own. Yeah, the hardest part is going to be draw the migration step. Who moves? All right, watch. Okay. All right, first step, pronation, then nucleophilic attack. Okay. All right, the migration step happening like this, forming double bond. Okay. So which bond breaks? You go from 5-membered ring to 6-membered ring. Can you see that? Look at recurrent ring expansion. Okay. So you can either pick this bond or that bond. You get these two options right there. You pick one. So I pick on the right one, it's just closer, attacking that red oxygen, and then loss of leaving group. See that? Okay, we're expanding the ring. All right, so let's redraw this. This is a 6-membered ring now, so no one draw like that here. Here we go. Okay, and depronation. That's it. Okay. No, that's how you use it. Now, we are focused on what we're interested in, who migrates. Okay, if you start with a regular, like a symmetrical ketone, I'll take a look. This one doesn't matter. If the right carbon migrates, you get this compound. See that? If the left carbon migrates, you get same compound. Nothing interesting. But when the ketone or aldehyde are not symmetrical, if the carbon migrates, take a look. If the carbon migrates, you're going to get this. If the phenyl migrates, you're going to get that. Different product now. We're going to look into who migrates. Okay, it's all about kinetic, who faster, basically. Okay, so all right, let's talk about who migrates right here. There's a theory why who migrates and what not. Okay, I'm going to show you 4 experiments, and let's see if you can see the pattern. There's a pattern. Are you ready? All right, put your pen down. I want 100% on here. Think. Okay, let's start with the first one. All right, adding peroxy acid now. Okay, so this is acetophenone. So you got option. If the phenyl migrates, you get this one. If the methyl migrates, you get this one. You know? Who migrates faster? Who migrates faster? The phenyl ring, the phenyl. Okay. All right, next. So right now we're comparing between a methyl and a phenyl. Next one. Primary carbon and a phenyl. All right. You're going to get phenyl migrates, you get that. Primary carbon migrates, you get that. Who migrates faster? Still phenyl. Okay. Phenyl is your reference point, basically. Next one. What am I doing here? Look. What type of carbons do we have now? Don't count that. Don't count. This is methyl. We don't call this primary. This is methyl. 1 carbon is this is primary. 2 carbon we call it secondary. This is secondary versus phenyl. See that? Phenyl migrate, you get that. Secondary, you get that. Who migrate faster now? Secondary. See that? Want to guess what's going on right down here? Next one. Tertiary. Guess who faster? If you have to guess. Tertiary. This is a migratory aptitude. Okay. Let me explain this way. This is our explanation. Okay. Why I think there are 3 theory. You need all 3 to be able to explain it, but we don't have time to teach you all 3. I'll just give you one of them. Okay. It's about when they migrate. Look at intermediate. All right. Right now we have a methyl and a secondary. Can you see that? Don't call that tertiary. This is secondary. Okay. Methyl and secondary. When they migrate, look what happened. This is a transition state. That carbon slightly positive right there. Okay. So it becomes slightly positive right there. Okay. We're gonna look at the carbon. If the methyl, same reaction, but methyl migrates, you have a slightly positive right there on the methyl group. And you guys know which carbon is more stable. The secondary carbon or the methyl carbon? If you don't know the answer, think this way. Imagine this were to be a carbocation and carbocation. Which one more stable? Secondary or methyl? Secondary, of course. Okay, this is transition state, so faster reaction right there. All right. Now, what about the benzene? Phenyl ring. Okay, the phenyl is different. I'll take a look. When phenyl migrates, okay, migrate better than primary in methyl, yes, we know, but not as well secondary and tertiary. The reason right here, when the phenyl migrates, we lost aromaticity. It's still better than primary in methyl, but seems like it's not as good as, not as stable as secondary and tertiary. Because we lost aromaticity right there, just for a split second. Okay, so that's why phenyl is slower than secondary and tertiary. Now you may ask, why the heck is hydrogen right there? Proton is unstable. We know that, right? The reason is when you do when you have hydrogen on one side, it undergoes different reaction. We call it different oxidation reaction, and that reaction is faster than any of this. We won't talk about in this course. I can talk about it. You're like, okay. All right. Last thing we'll do. Just tell me who migrates. Look right there. Just tell me who migrates. Okay. Oh, eyes up. Put your pen down. Put your pen down and eyes up. The top one, we're comparing a phenyl ring, phenyl and hydrogen. Am I right? Who migrates faster? Hydrogen. All you do, you just insert an oxygen between a carbon and that hydrogen. That's a product. That's the one who migrates. That's all you do. Okay. Next one. Oh, watch. Next one. What are we comparing? Tertiary and secondary. Do not call them quaternary. There's no quaternary. Okay. Okay. This is 1, 2, 3. Don't count the carbon. 1, 2, 3. Tertiary. That one secondary. Tertiary, secondary. Who migrate faster? Tertiary. All you do, put an oxygen right there. Right there. See that? That's a product. Does it make sense to you? All right. Last two. Which carbon migrates? I mean, what are we comparing? This one. We have right there. What do we call it right there? Secondary. 1 carbon, 2 carbon. That's a secondary. See that? And that right there, what do we call that? Primary. Good job. Who migrates faster? Secondary. What do you do? Insert an oxygen right there. See that? Right there. You get, yeah, that one. All right. Last one. Not that difficult. Look right here. It's just a structure thing, but it's not that complicated. Look at the that carbon first. What type? The what? Secondary. Good job. Secondary, and also an allylic position. Stabilized carbocation. You know. And what about the other? Primary. All you do, put a oxygen right there. The drawing is the difficult part. That one right there. We don't have exam on, no, we don't have the class on Monday, exam on Tuesday. Do we have class on Wednesday? Did you all read my email? Hey, did I send, no, hold on. I didn't send today, I sent Tuesday. Did I send to wrong people? I said on Tuesday. No one get it? What the fuck?
Who did you send that email to?
Are you serious?
Yes.
You were on Zoom. You don't get any email? What?
No email.
All right. You don't have an email. Okay, let me tell you this. Okay. Oh God. Let's tell you right now. Damn it. I thought you had it. Exam 2. Shh. What's the overall reaction? Hold on. All right. We have to learn. All right. We got 3 things to tell you. Listen. Shh. Or 4 maybe. 1 about exam 2. Okay. Exam 2 cover just this side. Just that. These are the basic mechanism, and I need that for later. That's it. Okay? All you need to know is just draw the mechanism. I mean, pretty good products, of course, but like the mechanism, that's what I want. You don't need to worry about the left side yet. Okay? Oh, that's on exam 2. Everything was chapter 16, 17, 18, and then 19 just on this side, on the right side. Okay, all right, that's an exam 2. Exam 2 on next Tuesday. Okay, cancel class on Monday, and I won't send the video. free day for you. We are about a week and a half ahead of schedule. And I planned that too. So you don't have to come on Monday. You have more time to study. Does that make sense? Okay. Now, Tuesday, exam time Tuesday is late at night. Don't show up on the next day. You have free day. Okay. But now, hold on. So it's a 75-minute. We can't lose that. So I'll send you a video. Video going to be on naming aldehyde ketone. Can you do naming? Okay. Naming carboxylic acid derivatives and a little synthesis. Just look at the hair now. How much we have left? Just that synthesis right there. Just a little bit left. That's gonna be on just that. Okay. All right. And on Thursday we come back. We'll come back with the complex spin multiplicity. Okay. All right. Summarize it. Exam 2. Just this side. After this side. Everyone follow me? Okay. Don't send me an email asking. On this side. Okay. The no class on Monday. Exam Tuesday, no class on Wednesday, but there will be video with the Wednesday. We'll come back again on Thursday on complex spin multiplicity.